we're going to do Introduction to Derivative Formulas. And then next week, we've got two big things. Wednesday, I'm going to give you quiz number 1. And it's a take-home. It'll be due the next class. We'll talk more about it when I give it to you, the rules for take-homes and stuff. And then Wednesday is also a project check-in day. Okay, so that's coming up pretty quickly. Project check-in day is a day that we spend in class working on the project. So in order to take as much advantage of that day as you can, you should have as much of the project done as you can get done. That way you can spend your time sort of comparing with your classmates, and then you can find places where, any place where you disagree and figure out who made the mistake, or maybe both of you made a mistake. And so here's the project suggested timeline. So by project check-in day, you should be around numbers 12 and 13, okay, for the project. And it actually involves 0 calculus up to this point, right? It's all just algebra functions and stuff. And then the next class, we're going to introduce the quotient rule, right? So you'll be able to use that for number 14. All right, any questions? Okay, so we can jump into today's lesson. So in this class, we're going to see our first derivative formulas. We saw a preview of the power rule last class. We derived the long way, the derivative of the square root of x. And we saw that its derivative was 1 over 2 square roots of x, and that agreed with the power rule that we're going to introduce today. So some notation. We're going to see this notation formally in a few classes, but this notation d dx of some stuff, d dx in front of a parentheses, that means the derivative of what's ever in those brackets. So if you have a newer graphing calculator, when you do n-deriv on your calculator, it gives you the d dx notation. Okay, if c is a constant, then the derivative d dx of c is 0. So let's sort of explore why that might be for a second. So here's a set of axes. A constant function would be like this, right? Constant function f of x equals c. If I pick any point on that line, any point, what's the slope of the function at that point? 0. So at every single point on the line, the slope of the tangent line is 0. So d dx of the constant is always 0. That make sense? Okay. So what's d dx of -7? 0. Good. All right, so now we introduce the power rule. D dx, the derivative of x to the n, is nx to the n minus 1, right? So you take the power, you bring it down, bring the power down in front, copy the x, and then subtract 1 from the power. So the derivative of x to the 6th, you're going to bring down the 6, copy the x, and reduce the power by 1. So the derivative of x to the 6th will be 6x to the 5th. So what these formulas do is they tell you the slope of the tangent line at any given x value. So if I wanted to know the slope of the line tangent to x to the 6th at 5, right, I would just plug a 5 into the derivative formula rather than going through that whole limit definition that we've been doing. All right, what is d dx of x to the -4? -4, copy the x to the -5. Well, here's a tricky one. D dx of the cube root of x to the 5th. It might be helpful if I rewrite this as just an exponent. What is a cube root? What power does a cube root correspond to? The 1/3. So this is actually x to the 5/3. 5 is the power, 3 is the root. Okay, so then I apply my formula, bring the power down, 5/3, copy the x. What's 5/3 minus 1? Yep, 2/3. There we go. So that is your power rule. So if I just go back for a second and look back at the constant rule again, the derivative of a constant is 0. That's actually a special case of the power rule. Because let's say I wanted to take d dx of -7 like I did before. If I think of it graphically, it's 0 because the slope of a horizontal line is always 0. But I could think of -7 as writing that as -7x to the 0. Because what does x to the 0 equal? 1. Anything to the 0 is 1. So if I write that as -7x to the 0, and then I apply the power rule, bring the 0 down, and I get 0x to the -1, which is 0. Right. So the rule for constants is actually a special case of the rule for powers. All right, now, also for constants, if c is a constant, if you want to take the derivative of a constant times a function, you can pull that constant right outside of the derivative, right? So just take the derivative of the function, and then when you're done with that, multiply by the constant. Okay. And in a special case, if you want to take the derivative of c times x, you just get c. Because what would the derivative of x to the first be using the power rule? 1, yeah, because d dx of x to the first, you'd bring the 1 down, copy the x, reduce the power by 1, 1x to the 0 is 1. So if I wanted to take the derivative of c times x, that's going to end up being c times the derivative of x, which is 1. C. All right, so in practice, what this means is just bring the constant outside and do the multiplication by the constant at the very end. So d dx of -2x to the 5th, that's -2 times d dx of x to the 5th, right? Just take the constant and do the multiplication at the end. So what's the derivative of x to the 5th? 5x to the 4th, so this is -2 times 5x to the 4th, which is -10x to the 4th. Now, we don't always write all that down. Very often, you'll get into the habit of just, when you bring the 5 down, you immediately multiply it by the -2 that's sitting there, and you get -10x to the 4th. You can do it in one step. But this is the reasoning behind the multiplication. Take the derivative, then multiply by the constant. All right, what's the derivative of -24x? -24. If you want to use the power rule, you can, right? Put a 1 on as the exponent, bring it down, you get -24x to the 0. But x to the 0 is just 1, so you just get -24. It's a lot nicer than doing the limit definition, right? Yeah. All right. One last special case rule. If c is a constant, then the derivative of c over x is the negative of that same constant over x squared. And we can think of it using the power rule. d dx of c over x is the same thing as d dx of cx to the -1, right? Dividing by x is the same thing as multiplying by x to the -1. Apply the power rule. You bring that -1 down and multiply by c, and you get -c. Copy the x, reduce the power by 1, and that simplifies to -c over x squared. So it's just a special case of the power rule. You don't have to memorize all the special cases because you can just apply the power rule and figure them out. But sometimes it saves you time if you know them off the top of your head. So d dx of 3 over x, that would be -3 over x squared, right, according to that rule. the negative of the constant over x squared. And d dt of negative 5 over t is the opposite, so I'm going to make it positive 5 over t squared. Yep. All right, so the sum and difference rules are exactly what you would expect, right? If you want to take the derivative of the sum of two functions, you can take the derivative of each function separately and add them together. Same thing with the difference. So if I want to find the derivative of f of x equals negative 5x to the fourth plus 7x squared minus 3x plus 2 cubed, I can apply the power rule to each term separately, right? So f prime of x, just look at the first term, negative 5x to the fourth. You're going to bring the exponent down, multiply by the negative 5, and you get negative 20. Copy the x, reduce the power by 1. Negative 20x cubed. Then move on to the next term, and you can just take the derivative of that one. The derivative of 7x squared would be 14x to the first, yep. The derivative of negative 3x, negative 3. The derivative of 2 cubed, why is it 0? 2 cubed is a constant, yeah. I was trying to trick you into trying to use the power rule, right? 2 cubed is just the number 8, and a constant has a derivative of 0. So I'm done here. I could write plus 0, but I'm not going to. All right, so there's my derivative of the polynomial that I graphed over here, negative 5x to the fourth plus 7x squared minus 3x plus 8. So what does the derivative tell you again? What is the derivative? Slope of the tangent line, right. So this tells you the slope of any tangent line you want. You just have to know what x value you're looking at, and you can plug it in, and it will tell you the slope of the tangent line at that x value. So I would like to find the equation of the tangent line at x equals negative 1. So here's my picture of f. Go to x equals negative 1. There's my point on the graph, and I would like the equation of the tangent line. Not just the slope, right, but the equation of that line. So what's the equation of a line? Y equals mx plus b, a plus bx, yep. So that's what I want. I want to know the equation of that line, which means I need to know its slope, and I need to know its y-intercept. Okay. I could use point slope, yep. Y minus y1 is m times x minus x1. You can use whichever one you're more familiar with. I'll do it both ways. Most people are more familiar with mx plus b, so I'm going to do that one first. We have a point, yep. Yeah. How do I get the slope of this tangent line? Plug negative 1 into the derivative, right? Because the derivative tells you the slope of the tangent line. So I know the x value is negative 1. That was given to me. Find the tangent line at negative 1. So my slope of the line I'm looking for, my m, is f prime of negative 1. So just plug a negative 1 in here, and I'm going to get 20 minus 14 minus 3. 6 minus 3 is 3. Okay. So this line here has a slope of 3. So if I'm doing y equals mx plus b, I now know m. Okay. And it looks like my y-intercept is somewhere between 15 and 20 based on my picture, but my picture is certainly not accurate enough to figure it out just by looking. So how can I figure out the y-intercept? Plug in a value for what? Yes. Okay, good. So what I need is a point, right? I need to know the coordinates of a point on my line. right? A point on the line. If I know the coordinates of a point on the line, I can put in the x coordinate for x, the y coordinate for y, and I'll solve for b. So I need a point on the line. Here's a point on the line. It's on the line and it's on the curve f, right? It's the point of tangency. So how can I find the y coordinate of that point? Jim, you just said plug -1 into the original function f, right? Because that point is not just on the line I'm interested in, it's also on the function f, because it's the point of tangency. So my point is going to be -1 f of -1, which is -1. If I plug a -1 in here, I get -5 plus 7 is 2, plus 3 is 5, plus 8 is 13. So now that I have a point on my line, I use it to figure out b. Right? So I put in 13 for y. Add 3 to both sides, and I get b is 16. So my picture was pretty accurate in that it just looked like the y-intercept was somewhere between 15 and 20. 16 works. So my final equation is going to be y equals 3x plus 16. So to find the equation of a tangent line, or any line, you need a slope and a point, right? And you can use y equals mx plus b, or it's actually a little bit quicker if you have a slope and a point to just use point slope form. Okay, so if you're familiar with point slope form, you can do that. If you're familiar with mx plus b, you can do that. I'm going to write out the point slope form. Ran out of room. I'll do it on the next slide here. Oops. So the point slope form says y minus y1 is m times x minus x1. M we know is 3. And x1, y1 is just the point that you know on the line. So this is x minus -1. And this is y minus 13. And then you can just leave it like that, or you could solve for y and you get the same line. So y is 3x. Distribute your 3 and you get plus 3, add 13 to both sides, and you get 3x plus 16. Same equation. So use whichever form of a line you like. Doesn't matter to me. And you can circle this and be done if you want to do that too. All right, so get as far as you can through the group activities. We're going to come back together with 15, 20 minutes at the end of class to start the next lesson, because the next one's a little bit long. Yeah. All right, so we're just going to start this demo. We'll finish it next class. So we're going to look at relative and absolute extrema, right? Maxes and mins for a function in context problems. All right, so for this function, I want to identify the x coordinates, just the x coordinates, of all the local maxima and minima. So first I'm just going to mark them, right? I've got one here, 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 and here, right? They're local maximums and minimums. Think of them as like peaks and valleys in a mountain range, right? They may not be the highest or lowest, but they're peaks, right? Peaks and valleys. So I've got 4 of them marked here, local maxima and minima. And what is the x value of this first one? B, right? So I've got B. And then the next one, it's got an x value of D. And the third one, F. And the last one, H. So we're just giving x values. So you should notice that at each of those local extrema in this graph, the set of all maxima and minima, the tangent line at each of those points is horizontal. So when you have a maximum or a minimum, horizontal tangent line. Okay. It is possible to have a relative extreme point, a maximum or a minimum, where the tangent line is not horizontal, where it's not flat. So for example, I've got this picture here, right, where I've got a minimum, but what is true about the tangent line or the derivative? What's true about the derivative at that point? It doesn't exist because it's a sharp corner, right? Okay, so our observations are summarized by this theorem called Fermat's theorem. It says if f has a local max or a min at an x value of c, right, then either f prime of c is 0, right? Either the tangent line is horizontal, or f prime of c does not exist. Okay? So either the tangent line is horizontal, which is akin to saying that its derivative is 0, right? Or f prime of c doesn't exist. We've got a sharp corner. We call x a critical number of the function f if f prime of x equals 0 or if f prime of x is undefined. Okay, so when we we look for places where f prime of x is 0 and where f prime of x is undefined, and it tells us that the only place a relative extrema might occur is at your critical numbers. So if I go back to the first graph of this section, I want to identify the x coordinates of all global maxima and minima. That is the very highest spot on the closed interval from A to J. Okay, so just going to erase some stuff here. All right, so I'm looking from A to J. What is the x coordinate of the very highest point in that entire interval? J. J. This point is the very highest point on that interval. It happens at the endpoint J. Oops. Sorry. From the picture, it kind of looks like that. There we go. Yeah, yeah. All right, so J is the very highest point, and what's the very lowest point on that interval? From A to J. D. Yep. So J is the max, J is the global maximum, D is the global minimum. Global max at x equals J. Global min at x equals D. Right? So when you're looking for absolute extrema of a continuous function on a closed interval, you just evaluate the function at each of the critical points and at the end points, right? So one of our global max was one of the end points of the interval. Our global min was one of the relative extrema, one of the valleys. And just grab the highest and lowest value. Pick the very biggest peak, or it might be the endpoint. All right, without using a graph to help us identify the peaks and valleys, I want to find the absolute extrema of f of x, which is this cubic polynomial on the interval from 1 to 5. So I want to find the biggest y value and the smallest y value between x equals 1 and x equals 5. All right, so local extrema, peaks and valleys, happen when the derivative is either 0 or undefined. So I have to find the derivative first. All right, so I'm going to apply my power rule. I bring the 3 down, multiply by 2, and I get 6. Copy the x, reduce the power by 1. 6x squared. Next term, I bring the 2 down and multiply by the 15, and I get negative 30. Copy the x, reduce the power by 1, so I have x to the first. And then for the 36x, I take the 1 on the x, bring it down, multiply by 36, copy the x, and reduce the power by 1. But x to the 0 is what? 1, so I'm not going to write that. Just a fancy form of 1. Okay, so there's my derivative. I need to know anywhere that this derivative is 0 and anywhere that that derivative is undefined, because those are potential maximums and minimums. All right, so this is a quadratic function. Is there any place where this thing is undefined? Any x value you can't plug in or the world will explode? No, quadratics are defined on all real numbers. So it's never undefined. So what I need to do is find out when it equals 0. At 1? let's see, I can factor a 6 out. So I could divide both sides by 6 and get rid of it. And then x squared minus 5x plus 6, that factors to x minus 3, x minus 2. So x equals 2 and 3 are two x values where the derivative is 0. Okay, what does a derivative of 0 tell you again? Why did we find out where the derivative equals 0? It's a minimum or maximum, yeah, because the derivative being 0 means that the slope of the tangent line is 0. And lines that have 0 slope are horizontal, right? So I found at 2 and 3 that I have horizontal tangent lines, okay? Which means I have a max or a min. Horizontal tangent line means you either get a max or a min, so you can draw a horizontal tangent line there. Okay. Yeah, so now you plug 2 and 3 back into the original formula to find out, we want to find the highest and lowest point on the whole graph, right? So I'm going to do f of 2 and f of 3. I'm going to get their y values. And then I also want the y values at the endpoints of the interval. So f of 1 and f of 5. The biggest one is going to be the global maximum on that interval. And the smallest one will be the global minimum, or absolute maximum and absolute minimum. All right, let me get a calculator for this. So I'm just going to type the formula into y1, 2x cubed minus 15x squared plus 36x. And then I'll just use my table. Put in 1, 2, 3, and 5. And my y values are 23, 28, 27, and 55. So where does my global maximum occur? 5. The very biggest y value on that interval is 55. It happens when x equals 5. They asked me to find the global max and min on the interval from 1 to 5. So I found the critical points in between. Gotcha. And I also have to look at the endpoints of the interval. Right, because this is a polynomial, and from 1 to 5, right, it could do any number of things, right? So I need to look at my 1 and at my 5, right? So I've got some critical points in between, and then I have to see if the endpoints are higher or lower than the peaks and valleys I find in between. I divided both sides by 6, because 0 divided by 6 is still 0. Yeah. All right, so this is a global max, or absolute max. Those words are used interchangeably, global and absolute. Okay. All right, where is my global or my absolute minimum? F of 1, yep. Global min. So you just have to be a little bit careful with your language. You say there's a global maximum value of 55 that occurs when x equals 5. So pay attention to what they ask for in a homework problem or on a quiz. If they ask for the maximum value, they want the y coordinate. If they ask for the location of the maximum, you give the x coordinate. Okay. The x coordinate is like the address. The y coordinate is the value. Okay. All right, I think I'm going to save the word problem for next class. You can go back to the activities you were working on before I pulled you back.